Good morning. Welcome to class. I'm glad you're here. Today we are actually skipping section 8.1.5, and that's because the nature of that lesson, the way it's structured, it would be really impossible to do it without everyone here in class. So we're going to move on to 8.2.1 today. And in a way, it's convenient because 8.2.1 picks up where we left off with section 8.1.5. How can I write the equation? So if you recall, yesterday we had discussed writing the equation of an exponential curve when you know, it's very obvious, you can see the y-intercept of the curve. That's the value when x is 0 and you know what y is. And it turns out that that's the 0th term when we're writing down the rule for the exponential curve. And then the other thing we have to do from there is work to figure out what the value of b is. Today, maybe we don't know what a is, right? By the end of the day, maybe we should be able to write the equation of an exponential curve in which the x-axis is an asymptote, or the same thing, the line y equals 0, right? Y equals 0 is the x-axis. Perhaps that's an asymptote for the curve. So let's start. How can I write the equation? Curve fitting. In this lesson, you will continue to work with exponential functions as you develop a new method to write linear and exponential equations given 2 points. So we know how to solve systems of equations, right? We know how to do that, and we know how to find the equation of a line given 2 points. Those two ideas kind of merge today in an interesting way. So, how can finding linear equations help you form strategies for finding exponential equations? In parts A and B below, you will help you answer that question. In the equation y equals mx plus b, which letters represent variables, which letters represent parameters? Briefly describe the difference between the two. So we have two variables, right? Our variables are x and y, right? Once we have a line set up, I can change x, and as I pick different values of x, the line that I have gives me different values of y. So x and y are my variables, m and b are parameters. And the parameters allow me to choose a particular line. So when I select m and b, I'm selecting the slope of the line and I'm selecting the y-intercept of the line. And with the exception of a vertical line, right, a line that goes straight up and down, I can pick any line on the Cartesian coordinate plane by just selecting different values of m and b. Once I've done that, once I've selected a particular line, then I'm giving it values of x and it's giving me values of y. If we went to Desmos real quick, in Desmos, I can type in the equation of a line. I can type in y equals mx plus b. Now, Desmos knows that these two things, m and b, it doesn't recognize as variables, right? Y is the variable, that's the up and down, these values, and x is, of course, the horizontal ones. So it sees m and b, and it's like, hey, what are those? And it asks to set those up as sliders. So I say, okay. As soon as I do that, you can see that at this point, m and b, once I select them, they are held static for a line, right? For a line, they don't change. This line right here is always going to have m as 1 and b is going to be 1 equal for this red line. Now, as I move my cursor up and down on here, you can see the first number there is my x value and the second number is my y value. And as x changes, y responds and gives me different values back. So x and y are my variables and m and b are my parameters. Next, it says, what is the equation of a line with a slope of 3 that passes through this point? Okay, so I know that my slope, I know my slope, which is represented by the parameter m equals 3. And I also know that I have a point, an x and a y value, an x and a y value that represents a particular point that lives on that line. There are lots of lines that have an equation of 3, or have a slope of 3. Lots of lines have this slope, right? And there are lots of lines that go through this point. But it turns out there's only one line that has both of those properties together. And the way that we've typically done this is we've considered y equals mx plus b, and we've replaced the one parameter we know, right? We know the slope parameter in this instance. We've replaced that with the number 3. And we've also replaced the y value from our point, so we would use 19. And we've also replaced the x value from our point, which is 5. And when we replace those things, the only thing that we have left is this one parameter that we don't know. We don't know what b is. So 19, of course, is 15 plus b. Therefore, 4 is the value of b. The equation is then y equals 3x plus b. And 3x plus 4. And I know this is the correct line for two reasons. First of all, it clearly has the correct slope, right? I can see that the slope of this line is 3. The other thing that it has is the fact that if I plug 5 into this equation, right, it gives me back the value of 19. 3 times 5 is 15 plus 4 is 15. So when 5 goes in for x, 19 comes out. So I got it, right? I got it. Let's move on. Can you use similar ideas to find an exponential equation? Okay. In the equation y equals ab to the x, which letters represent variables, which are parameters? So in this one also, x and y are variables. And once we're looking at a particular exponential curve, I pick values of x, right? I can change that value of x, and then the curve gives me back the value of y that corresponds to it. A and b are parameters. And more specifically, a is the 0th term. If I'm speaking of a geometric sequence, I could also say it's the y-intercept, right? It's the value I get when I put in x as 0. And b is the common ratio or the multiplier. While trying to find the equation for the graph in part A of problem 66, shown again, Errol stated, I think A must be 7 because the y-intercept is 0, 7. Do you agree? Justify your answer. Well, absolutely, because when I plug in that x, if you think about this, when I plug in y equals ab to the x power, when I plug in that x is 0, right? X is 0. When x equals 0, that makes, I'll say this, if x is equal to 0, then b to the x must become the number 1. And if that equals 1, right, then all I have is just 1 times a, right? So it very clearly becomes the fact that this would become 7. So when x is 0, y has to be 7. So we agree with that. Okay. But we still don't know what b is, Errol noticed. His teammate Sandy had the idea. Okay, so this is pretty much a rehash of what we did yesterday. So she wrote this, and if you'll notice what she did, right, we had the point 7, 56. 7 was my x value, and 56 was a y value for another point that was somewhere on the graph, right? So we know what our 0th term is. We know that this, right? I'm sorry, that's not correct. This is not correct. let me erase this. Let me start over again. Y equals AB to the x power. We know that A is equal to 7, and we have this point that lives at 356, 3 comma 56. So what we know, let's get this right, Mr. Roberts. We know an x and a y value, right, from a particular point, and we also know where we're crossing the y-axis. So we can plug these values in to this equation. Y becomes 56. A, we know, is the value 3. And x is the number 3. So we end up getting 56 equals 7 times b to the third power. And yesterday we discussed how we solved this equation, right? We did two things. The first thing we did was we divided both sides by 7. So this becomes 56 over 7 is b to the third. Therefore, 8 is b to the third. And if I want to solve this equation, I can raise both sides of this to the 1/3 power, And 8 to the 1/3 power, I'm told, is the number 2. By the way, a fun fact, that 8 to the 1/3 is equivalent to a cube root of 8, right? This is alternate notations. 8 to the 1/3. In fact, this denominator right here is a root index, but I digress. So we get that 2 is equal to b. So now it says use a and b to write the equation of this graph. Does it agree with the equation you found in part? Yeah, okay, so now at this point we can write the equation, right? Y is equal to 7 times 2 raised to the x power. And it fits exactly what we observe with the graph, right? If I was to look at this in a table of values, when x is 0, we get the number 7 from it. If x is 1, we get the number 14. If x is 2, I double it, I get the number 28. And if x is 3, we're up at 56. And we can see that it's hitting the 2 points that we see on the graph, right? It's hitting this y-intercept at 0, 7, and it's also hitting the other point, the additional point at 3, 6. So we know this is correct. Mitchell was helping his friend work on his algebra homework. They were trying to write the equation of a line that passes through 2 points. Okay, so we're setting the stage now for how we proceed if we do not know the y-intercept. So right now we're reviewing kind of what we did with finding the equation of 2 lines. And Mitchell had an idea about finding the linear equations. Look, he said. Now, I'm not going to read what he does, but I'm going to come over here and show you essentially what happens. So we have 2 points. We have the point 5, 15, and we have the point 3, 7. This is not something that I thought of. This is not something I did, but I think it's pretty insightful. If I think about this, I have this relationship y equals mx plus b. And I can write 2 equations using the x and y value from the 2 points that I have. So for example, one of the equations I could write is 15 equals m times 5 plus b, and that's based on the first equation. And the other equation I can write is 7 equals m times 3 plus b. And that's based on the second point that I have. So when I do this, right, what we end up getting is a system of equations. I've got 2 equations that are based on, the first one is based on this point, and the second one is based on this point 37. And because I have these now, I can solve this as a system of equations, right? And in fact, to me, just looking at it, I think I might, because I can see that I've got this b and b, I think I might solve this by simply multiplying one of the equations, it doesn't matter which one, by the number -1. So if I took the bottom equation and I multiplied every term by -1, I'll rewrite the top equation for convenience. It's going to become 15 is equal to 5m plus b. I just reordered those. And the other equation is going to become negative 7 equals negative 3m and then minus b. So by multiplying the second equation by negative 1, this is now set up for elimination. And because I have equal things, and I'm going to add to that both sides equal things, I'm going to get equal things. Over on the left-hand side, if I take the number 15 and I subtract the 7, I get the number 8. Over on the other side, I've got 5m, and I'm going to add to that a negative 3m. I'm going to get just 2m. And my b's are gone, right? b plus negative b is 0. So because of this, I end up getting that a, or m rather, my slope parameter is 8 divided by 2. Therefore, m is equal to the number 4. That's an interesting way to find the slope, right? I can confirm that it's correct by looking at my original points, and I can say the slope is change in y over change in x. Change in y I could write as 15 minus 7 over 5 minus 3. 15 minus 7 is 8. 5 minus 3 is 2. I get a slope of 4. So it works, right? Solving a system of equations to find the parameters of this line. Now that I know what m is, right, I can plug that into either equation, the top or the bottom, and figure out what b is. I'll use the top equation. 15 equals 4 times 5, 20, rather, plus b. So if I subtract 20 from both sides, I get that negative 5 is the value of b. And just for fun, I'll do that with the second equation as well. It says 7 is equal to 3 times 4 is 12 plus b. If I take away 12 from both sides, I get negative 5 is b. So I know the equation of this line because I now know both of the parameters. I know the slope parameter is 4, and I found twice that the y-intercept parameter is negative 5. So the equation of the line that goes through those 2 points is y is equal to 4x minus 5. And as a triple check, I feel like I've been checking a lot. I could plug in x from the first point, 5, and I do get indeed 15. And if I plug in 3 into that from the second point in, it does give me back 7. So this is a different strategy. It's not how we've solved it's not how we found the equation of the line before using a system, but this might be useful today. All right, so let's go down. And I've just explained what Mitchell was talking about, how he used a system of equations to find that line. So next, will Mitchell's method work to write the equation of a line through any 2 points? Justify your answer. You know, the one place where I think this could fail, if I had let's see that this is the y-axis, and this is the x-axis. If I have a line that has these 2 points, let's say this point is x is 5, y is 6, and I'll say here x is 5, y is negative 2. I think a vertical line, I don't know. I do not know. So if I wrote the equation line, I would write y is equal to m times x plus b, and the other equation is going to be y is equal to m times x plus b. Oh yeah, I see what will happen. I think this vertical line would be a problem, because if I multiplied the second equation by negative 1, this equation would become 2 equals negative 5m minus b, and the top equation is still 6 equals 5m plus b. And what happens when I combine those, on the left-hand side I get the number 8, and over on the right-hand side I get 0. So I think as long as the line is not vertical, this method should work. It's interesting though, because if you end up getting a vertical line, as soon as I see that I have the same x value for 2 points, I immediately am thinking, oh, okay, no matter what happens, x will be 5. And that's the equation of that vertical line. But other than that, his method worked very well, I think, for finding the equation of any line. So what we're going to do now is it says, use Mitchell's method from problem 92 to write the equation line that passes through these 2 points. So I want you to do this. So go ahead and pause the video, find the equation of that line, and then we will move on. So I trust that you did pause and do this, and if you did, you should get y equals negative 3x plus 9. I have to be honest, it took me 3 attempts to get it. I knew every single time I was wrong, because as I plugged in my x values, I wasn't getting the correct y values. But I kept looking at it and working through until I found my error. So this is the work that I left off at, but maybe ignore my work and go back at it, because really to move on and not know that you can do this reliably is kind of a problem. So if you're good and you're satisfied with that, let's move on. Next problem. Mitchell thought maybe his method from problem 92 could be used to write exponential equations of exponential functions. He wondered if he could write the equation of an exponential function that passes through 2, 144, 6, 7, 29. What is the general form for an exponential function that has an asymptote at y equals 0, the x-axis? So that would be y equals a times b raised to the x power. Use these 2 points that you know to create a system of equations. So if I was to do that using these 2 points, right, this first one here is that one, and the second one I'll box in this green. Let's write we'll do the green one, we'll do the orange one first and then the green one. So the first one I'm going to write is y, which is 144, equals, I do not know a, I do not know b, to the x power, x is 2. Okay, so the second equation I have is that 729 equals a, okay, I do not know a, b, I do not know b, but I do know that my exponent is the number 6. Okay, all right, so here's my system of equations. How could I solve this? Well, looking at it, the first thing that I think of is I'm not going to be able to get opposites and make things cancel here, but I can solve each equation so that a is by itself, and then I could solve it using the equal values method. So in each one, if I was to get a alone, this top equation, I'm dividing both sides by b squared. It's going to become 144 divided by b squared equals a. And the second equation is going to become 729 divided by b to the 6th power equals a. Well, in the context of this problem, right, it is the case that a equals itself. So I can say 144 divided by b squared is equal to 729 divided by b to the 6th power. Isn't that fun? Isn't that fun? Well, the next thing I think of is, looks to me like a nice place to apply fraction busters, right? Because both of them have denominators. So I think what I'm going to do is multiply both sides of this equation by b to the 6th power, b to the 6th. And I'll put that in the numerator. So, I mean, well, because I'm multiplying it, that's why I'm putting it in the numerator. If I do that, I get 144 b to the 6th power over b squared equals 729 b to the 6th power over b to the 6th power. Well, I can see on the right-hand side I have this giant 1 in the form of b to the 6th over b to the 6th. So, and on the left-hand side I can simplify because I've got 6 factors of b in the numerator and 2 factors of b in the denominator. So this equation becomes 144 b to the 4th power equals 729. If I divide both sides by 144, I get that b to the 4th is 729 over 144. So let me grab my calculator. 729 divided by 144. Uh-oh. Boy, I didn't get a pretty number. I hope I haven't made, I could have made a small mistake somewhere, and we'll find that out in a moment. But I got that b to the 4th power equals 5.0625. So if I want to know what b is, I'm going to take the 4th root, I'm going to raise both sides to the 1/4 root. So this side gets raised to the 1/4 root, this side gets raised to the 1/4 root. So if I take my 5.0625 and raise that to the 0.25 power, that looks better. I mean, I get b is equal to 1.5, which is the same as 3/2 because I'm always biased towards rational numbers, but this is good too. So at this point, I feel like maybe we know what b is. And then I'm like, well, man, what's a? I know b, I know my multiplier, but I don't know my 0th term. Well, I could go to a table of values and I could figure out what a is, but also it turns out that I ended up writing 2 equations to find out what a is, right? So remember, if b is equal to 1.5, I could find a in 2 ways. Let me fire up the calculator. There it is. So what I'm going to do is I'm going to take that 1.5 and put it into both equations. So the first equation, I'm going to have 144, and I'm going to divide that by, and I'm going to use parentheses, 1.5 to the 2nd power. So exponentiation comes first, so it is going to square the 1.5, take that result and take 144 and divide it by the result. And I get b is 64. I know I get a is 64. Let's see if we get the same thing from the other equation. So the other equation is the 729, and I'm going to divide that by b to the 6th power. Okay, so I've got my 1.5, and I'm going to raise that to the 6th power. When I do that, great news, I also get that a is 64. So because of this, because I know my 2 parameters, I can now write the equation, the exponential curve that goes through these 2 points. It should be y is equal to a, the number 64, times b, 1.5 or 3/2 raised to the x power. Now, as a double check, you might want to go through and see if you put in 2, does it give you 144? And if you put in 6, does it give you 729? But I'm fairly confident that it does. All right, so we're going to finish this, and we're almost at 30 minutes. We're going to finish this by having you do both of these. And I would like for you to pause the video right now, do both of these, and then I will put the answers up to both so that you can check. Of course, you should be able to check by putting in -1 and making sure your first answer gives you -2, and 3 should give you 162. But short of that, I'm going to show you the answers anyway. So everyone pause. Okay, so for the first question, part A, you should have gotten you should have the equation y is equal to -6. Yes, your 0th term is -6. And then times 3 raised to the x power. Your multiplier was 3. And for B, you should have had y is equal to 7 times 0.5, or you could have the 1/2 there, raised to the x power. So if you're, I'm sorry, I covered those up. So if you're stuck, you didn't quite get those, you need help, make sure you stop in this afternoon and talk to me. Thanks for joining class. I will see you again tomorrow on a not a short Wednesday, on a distance Wednesday. Also, I'll remind you that I did say that on this distance Wednesday, one of the things you'll be able to do tomorrow is do your test corrections for Chapter 7. And if you wish, I will have a point recovery quiz that you can take remotely. All right, talk to you soon.